Welcome back. So, we are in the middle of the discussion of this scaling of the turbulent flow, and we are looking at wall bounded flows and shear flows. So, we looked at the effect of the roughness also. Now, we will continue from there and what happens in the boundary layer, and you have turbulent boundary layer over flat plate, you have turbulent pipe or channel flow, you have wall roughness. So, if you sort of combine them together, they will get into three different layers. One is the inner layer, there would be log layer, overlap region and the outer region. So, this is how the complete velocity profile in the boundary layer and obviously you have in a smooth wall you have some viscous sublayer, buffer layer and viscous wall region. So, in the inner layer this is the law of the wall, and when you come to the log region there would be log law plus wake, law of the wake, and then you come to the outer layer where you have a velocity defect law, and this is what it combine everything together. Now, one important thing is that we can find out the skin friction coefficient of the boundary layer for zero pressure gradient case. Now, we have the velocity defect law, which is the ratio of u naught by u tau, which is order of 1 by kappa ln delta u tau by nu plus b 2 pi by k, and skin friction coefficient in the turbulent region for the smooth wall is defined as tau w by rho u naught square by 2, which is essentially like this. So, if you plot CF versus REX, this is how it moves, and when it becomes turbulent, this is how. Now, in the laminar region, it would be nicely one can find out it would be order of points REX, and that is the curve which shows that in the laminar, but this is the zone where it trips and then it becomes turbulent, then it follows like that. Now, moving ahead, we can look at the kinetic energy of turbulent flow. What we have already seen that there are large eddies which are actually the energy containing eddies, and the energy transfer from the large eddy to the smaller eddy. So, there is and then from smaller eddy through dissipation it dissipates. So, this is how the energy cascading takes place. So, we can find out or estimate the kinetic energy. So, transport equation for kinetic energy of the mean flow, we can same transport equation for fluctuating flow and normal Reynolds stresses. So, these things we can actually, now we first look at mean kinetic energy budget. So, mean kinetic energy budget, what we look at. So, this is we can derive the transport equation of mean kinetic energy, let us say E, which is ui square by 2. So, we can multiply the momentum equation by ui bar, and then we get ui bar del ui by del t plus ui uj del ui by del xj minus ui by rho del xi nu del 2 j by xj minus ui bar del xj uj prime. Now, the diffusion term we can rewrite like ui nu del 2 ui bar by del xj, which we can write like del xj nu del e by del xj minus nu by del xj square, and the Reynolds term also we can rewrite, which is minus ui del xj of ui prime uj prime, which is now del xj of minus ui bar ui prime uj prime plus ui uj prime del ui by del xj. Now, if I put these things into the previous equation, that will get me d bar by dt plus uj by del xj minus ui by rho del p by del xi plus del xj nu by del xj. Ui prime plus ui uj prime minus nu del xj square. So, that is what we get for mean kinetic energy. Now, here we can say, let us say in the right hand side this would be the term 1, this whole thing we can say it is a 2, this guy 3 and this guy 4. Now, term 1 is energy production by pressure gradient, then term 2 is the spatial distribution of the energy by viscous and turbulent diffusion, which means if I integrate over volume by Tj dV, which will get me the surface integral of Tj Nj dA, which is 0 when Tj equals to 0 at A. Now, term 3, which is in this term, which is a loss of energy by Reynolds stress. So, using the Boussinesq hypothesis, one can write that by del ui by del xj minus 2 nu t Sij bar Sij bar, which is less than 0, where Sij is half of del ui bar by del xj uj by del xi, which is the rate of strain tensor of the mean flow. And term 4, which is again loss of energy by viscous dissipation. So, one can estimate that one by minus 2 nu Sij Sij. So, these are the different terms in that kinetic energy equation. Now, if we look at this mean kinetic energy equation for plane channel flow, so that gives me, this is a pressure gradient term, transport term, Reynolds stress term, viscous dissipation term, and if you plot this budget term, that means this is the individual term. So, you can see the contribution from each of these terms, I mean due to pressure gradient or the transport and all these things. Now, we can look at mean turbulent kinetic energy budget. So, we can derive this transport equation from the kinetic energy, which we have defined by 2. So, this is mean turbulent kinetic energy budget. So, turbulent kinetic energy would be this. Now, we can subtract the mean momentum equation from the momentum equation and multiply with the ui prime, and take Reynolds averaging. So, we first subtract mean momentum equation from the momentum equation and then multiply by ui prime and take Reynolds averaging. So, what we get del k by del t plus uj del k by del xj minus ui prime uj prime del xj plus del xj where nu del k by del xj minus uj prime half ui primes rho p prime minus nu del u prime by del xj which is square bar. Now, again we can have, this is the term 1, this term is 2 and this is term 3. So, term 1 is the production of turbulent kinetic energy by Reynolds stress on mean flow. So, turbulent flow is essentially unstable. So, instability process transfer of energy from mean flow to large eddies. Now, term 2, which is a spatial distribution of turbulent kinetic energy by viscous diffusion and fluctuating velocity plus pressure, and term 3 is the loss of turbulent kinetic energy due to viscous dissipation. Now, for a plane channel flow, if you look at the mean turbulent kinetic energy, so this is the Reynolds stress component, this is transport component, distribution component, and you can look at the effect of different budget terms for plane channel flow. So, once we get this, now also you estimate the local energy equilibrium. So, where the shear production by the Reynolds stress at certain y plus, and you have dominant balance in the log layer, where this is the production of by action of large eddies which contributes to maximum of shear stresses, and this is the dissipation at small scale. So, this production term is based on Kolmogorov theory, where nu 2 is proportional to epsilon to the power 1/3 and this, where so that means in log layer there could be a balance. Whatever is the energy produced by the large eddies, this should be dissipated by the small eddies. So, we can apply these turbulent kinetic energy bodies for one equation model. So, the macroscopic velocity scale u is sum by k and macroscopic length scale is Lm, which will get us nu t equals to ul, which is c prime mu k Lm. Now, we can have an turbulent kinetic energy transport equation which is in terms of del k by del t plus uj by del k by del xj minus ui prime uj prime sij plus del xj, which is nu del k by del xj uj prime half ui prime square minus 1 by rho p prime uj prime minus nu prime by del xj square. So, this is estimated as 2 nu t sij bar. This guy is estimated at nu t by sigma k del k by del xj with sigma k equals to 1, and this is CD k to the power 3 by 2 Lm. Now, local energy equilibrium between production and dissipation, in that concept we can write that C mu prime cube by CD Lm square by 2 Sij square, which is Prandel's mixing length hypothesis. So, advantage of this one equation model is that it accounts for non-equilibrium effect. So, that is one of the advantage, but the biggest disadvantage is that mixing length must still be specified. Now, we can have this one equation coefficients, that we can consider this logarithm layer of turbulent plane channel flow, where u prime v prime is approximately u tau square del u by del a. So, this is the coefficient for the C mu. Now, in log layer, due to local energy equilibrium, you get C d equals to, or C mu equals to 0.17. Now, we can find out the eddy viscosity per velocity component. Now, for individual velocity component, kinetic energy would be u alpha prime by 2. Now, you can subtract the mean momentum equation from the momentum equation and multiply by u alpha. So, we get this equation. So, which is in terms of which we have got del k alpha by del t plus u j del k alpha by del x j equals to minus u alpha prime u j prime by x j plus del x j minus u j prime half prime square 1 by rho p prime delta j alpha plus nu del k alpha by del x j plus 1 by rho p prime square. So, a right hand side you got term 1, term 2, 3 and 4. So, you can find out the energy per fluctuating component like this. For a plane channel flow, if kx 0, then this would be 0. So, you can put it, this is the shear production component, these are the transport component, pressure strain term and viscous dissipation. So, the shear production feeds to kx, which is anisotropy of large scale motion. So, that essentially tells you how much anisotropy is there, and pressure strain redistributed the energy of u to other velocity component through this. Now, we can look at the different budget, like budget of kx, ky, kz and all these details. So, this is taken from this multiple literature where people have looked at for channel flow in details, and they computed individual budget terms and all these things. Now, if we look at for plane channel flow and energy conversion. So, we can say that, say this is my u square by 2, this is mean kinetic energy which is fed u bar by rho dpw by dx, then it goes to a term which is essentially u prime square by 2, and that minus p prime by rho del w prime by del z, that get you by 2 minus p prime by rho del v prime by del y, get you the v prime square by 2. So, that is another block where u prime v prime del u by del y. Now, here this is nu del u prime by del y square, then this minus nu del u prime by del x j square, then this del v prime by del x j square, and this one also minus nu del w prime by del x j. So, all this will contribute to the one single component is the internal energy, which is Cb T bar in case of ideal gas. So, this is how the complete picture of the energy conversion look like for a plain channel flow. Now, we move to the another topic where you have the density which varies due to temperature. That means the between two parallel plates we look at Rayleigh-Bénard convection. So, we have two parallel plate plus G, this is G direction, axis x, y, z, and this is how my G is going to act. So, this kind of things one can observe in atmospheric boundary layer, where heating of earth's surface by short wave radiation from sun during the day, cooling by long wave radiation during the night. Now, here Bouguereau's approximation would be required. So, the temperature variation is connected with the pressure and hydrostatic variation, which is like this, and the Bouguereau's equations we write del u by del xi 0 del u by del t plus uj del ui by del xj 1 by rho xi minus alpha theta by theta naught gi plus mu by rho 0 and del theta by del t plus uj kappa del 2 theta by del a square. So, alpha equals to 1 for ideal gas, and this is the term which is known as buoyancy effect. So, we have already looked at this equation. Now, how temperature affect? This is a parallel plate and these are the two different temperature it has, and you can see how basic state one can assume the linear temperature profile, and based on linear normal mode stability analysis one can do and find out the Rayleigh number, and this is how the experimentally observed flow pattern in these things. So, it goes through multiple bifurcation before it becomes fully turbulent. So, this is another area where, and you can see these are the some of the example of this Rayleigh-Bénard convection in atmospheric cloud, where you can see these things. Now, we can estimate the turbulent kinetic energy budget including buoyancy effect. So, the derivation would be similar and we have already got the equation. So, but we will rewrite it, but there will be effect from the temperature gradient. So, this would be ui prime uj prime del ui bar by del xj plus g by theta 0 W theta plus the transport term and the epsilon dissipation term. So, this is an extra term that you get. So, this again the term 1, which is a production by the Reynolds shear stress. This is the called the buoyant production or destruction of turbulent kinetic energy by gravitational forces. Now, what is buoyant production or destruction? So, the Boussinesq hypothesis says that W prime theta prime would be gamma t del theta by del z. So, this is a typical gradient diffusion hypothesis in turbulent heat flux, where gamma t is approximated as nu t by sigma t, where sigma t is the turbulent Prandtl number, nu t is the turbulent diffusivity. So, there could be two different cases, where one case this is an convective turbulence. So, g by theta 0, W prime this would be minus g gamma t by theta 0 del theta by del z greater than 1. So, this will be buoyant production situation, or you can have a situation where g by theta 0 W prime theta prime is minus g gamma t by theta 0 less than 0, which is buoyant destruction. So, we can look at this production and destruction term, the buoyancy effect. Now, the other like buoyancy versus shear and all these things that we will discuss in the next lecture. We will stop here today.